Hello and welcome to this video on half-life and the random nature of radioactive decay, where we'll be looking at how to measure decay, what half-life is, and how to calculate it. The activity of a radioactive source is measured in becquerels, capital B, lowercase q. This is the rate at which a source of unstable nuclei decays. The count rate is slightly different. This is the number of decays recorded by a detector each second. Count rate can be recorded by a Geiger-Müller tube, which detects the radiation, and a scalar counter, which displays the result. Because the radiation given out by the decaying isotope goes out in all directions, not all of the radiation is detected by the Geiger-Müller tube. For this reason, the count rate is always lower than the activity. Radioactive decay is random. We can't predict which nucleus will decay next. But if we measure the count rate for a long enough amount of time, a pattern emerges, and from that data we can find the half-life. The half-life of a radioactive isotope is the time it takes for the number of nuclei in the isotope to halve, or the time it takes for the count rate, or activity, from a sample containing the isotope to fall to half of its initial level. For example, if we take a sample of radioactive nuclei, after one half-life, and let's say the half-life is 20 minutes, half of the nuclei will have decayed into something else. After another 20 minutes, half of the original isotope that was left will have decayed, and after another 20 minutes, a further half will have decayed. The half-life of a radioactive isotope can be found by using a decay curve graph like this one. The data can be obtained by recording results of count rate from a Geiger-Müller tube placed near a radioactive isotope over a period of time. Plotting count rate against time gives a graph with a nice smooth decay curve, and a half-life can be found using the following method. Read the highest value from the line on the graph, in this case it's 80. Halve that value, so 80 divided by 2 is 40. Draw a line from 40 to the line on the graph. Draw downwards to the time axis. Read the value from the time axis, and that's your half-life. You can check this by looking at the value from the second half-life, so 40 divided by 2 gives 20, and if again you go across to the decay curve and down, that will give you the half-life. And you can check it a third time by going 20 divided by 2, which gives 10, go across to the line and down, and that will give you verification of the half-life, and it's all 1 day. For some uses of radioactive isotope, it's better to have a short half-life, and for others a longer half-life is more suitable. An isotope with a short half-life gives out a lot of radiation in a short space of time, but the levels of radiation quickly decrease. An isotope with a long half-life decays slowly, so less radiation will be given out per second, but the radiation will be given out over a longer period of time. These things have to be considered when choosing a radioactive isotope for a job. For example, you probably don't want an isotope with a short half-life in your smoke alarms. They would give out more radiation than is needed, and you would have to change your smoke alarms when the level of radiation is too low for it to work. The most often used isotope in a smoke alarm is an alpha emitter with a half-life of 432 years. This means after 432 years, the activity of the isotope will have reduced to a half. This is much longer than the expected life of the alarm, so it's a suitable choice. In an exam, you may be asked to calculate the half-life from some data. So this is an example of how to handle that type of question. A radioactive isotope has an initial count rate of 32 counts per minute. After 2 hours, the count rate is 8 counts per minute. What is the half-life of the isotope? Well, starting with 32 counts per minute, after one half-life, that value will have halved to 16 counts per minute, and after a second half-life, that value will have reduced to 8 counts per minute, which is our target from the question. That means that we've gone through 2 half-lives in 2 hours, and 2 hours divided by the 2 half-lives means that the half-life is 1 hour. In this question, you are given a table showing the half-life of some radioactive isotopes. The question reads, which one of the isotopes in the table could form part of a compound to be used as a tracer in medicine? Explain the reason for your choice. And the question is worth 3 marks. A medical tracer is used in medicine to perform tests. A compound containing a radioactive isotope is injected into the patient's body. As the compound moves around the body, it decays and emits gamma radiation. This radiation can be detected outside the body and can give doctors information that they need about the patient's condition. So we need to use that information and look at the suitability of these different half-lives. Magnesium-27 has got a half-life of 10 minutes. That's too short. It's not long enough time for the tracer to move around the body and for the readings to be taken. Two at the bottom, sulfur-35 and cobalt-60, one is 87 days and the other is 5 years. These are both too long. The patient will be exposed to ionising radiation for all of that time, and that could be dangerous for the patient. Which means sodium-24 is the correct answer. You get a point for saying sodium-24, and the other 2 points are for the explanation. Long enough for the tracer to circulate the body and take readings will give you a point. And the third point is for saying that it's short enough that the isotope will quickly decay to insignificant levels of radiation. And that's it for this video on half-life. Thank you very much for listening.